Okay, so I think we can start. We continue today discussing these four classical models of a hyperbolic space. So let me like highlight the topic. So okay, models of HD, right? And let me remind that we have four models. The hyperboloid model with this metric rho h, where the hyperbolic cosine of rho h, so the distance between these points satisfies the following identity, this minus x, y. Also, we have the projective Klein model rho k. The formula, I think that I didn't write it down last time, but we will do it today. So this is the hyperboloid model. This is projective or Klein model. The ball model BD and the metric rho b, and the last one is UD and rho sub u, right? And let me immediately, so let me write, okay, let me draw the picture here just to remind how it looks like. So we have an isotropic cone, right? So those vectors satisfy x times x is equal to 0. Here we have the Lorentzian. So the Lorentzian scalar product is of signature and 1. So here we have negative, right, in top and bottom parts. And we can choose. So this is my axis x0, and my hyperbolic space is the cone. Well, it's actually the hyperboloid. So it's the upper half sheet of this hyperboloid. So this is my HD. And we have a few hyperplanes, right? So we had a hyperplane, which is like in a fine chart, x0 is equal to 1. So it touches. This is actually, for us, this will be an important point. So it touches this hyperboloid in this point, at this point, and also there is another, right? There is another. Okay, let me slide 3. So there is another plane, hyperplane parallel to that one, and this is the hyperplane x0 equals 0, right? And we have some other models here. The first one is the ball model in this hyperplane. So generally, remember, this is a so this is KD. This model is obtained by using the projection, the central projection. I'm out of colors. Okay, I will take some here. So the projection is just the central one. I'm taking the point from the ball, right? Taking the ray from 0 to the point x, and I'm obtain the point sitting in this hyperplane, and this will be definitely, so the image of this projection definitely sits in the unit ball in this model. Another model, let me remind again, the picture is obtained via the stereographic projection. So I'm taking, okay, let me denote this point as, what is the best notation? I don't know. Let me denote it by A, right? So A is my point with coordinates 1 and the remaining coordinates are 0. So the scalar product is, try to remember that the scalar product is with, let me write it down somewhere here, right? This is important. So x times y is equal to minus x0, y0 plus x1, y1 plus and so on. Xd, yd, right? This is our scalar product. Yeah. So the scalar product of A with itself is definitely -1. And I'm taking the point here, which is called -A, right? I can also actually choose just vectors E0 and so on, ED, and then I will denote it as E0, right? There is another possible notation for that point. Okay, so the projection from HD to BD then goes as follows. It's stereographic projection. I'm taking this point. Oh, no. So it should go over here. And it gives me another. Yeah, so I have the unit ball here. And this gives me the ball model BD. And my image is like somewhere here, right? This is the image using the second map. So this gives me another model. And finally, to get from BD to UD, I need to apply the inversion. So there is another model UD, which I'm going to describe as points from, okay, we will usually encode them like this. They will look like points, okay, maybe better to use YT, where Y is from RD -1, and T is a positive number, positive real number, right? This is my model upper half space. So generically, it looks like that, yeah? And this is basically the axis T, right? So that's the picture. Now about the formula. So I'm moving this to the top so far, and we will write down the distances. Okay, so here, yeah, by the way, no, I will use this board again. So the coordinates, so probably let me define the projection. Okay, let me denote the projection. So P is the projection from HD to KD, right? And let me denote the point, the image. So my P of X is the X hat, which is the pair 1, since the first coordinate here is 1, right? Okay, the 0 coordinate is 1. And then I'm getting some X bar which is from, okay, which basically the point of the unit ball. So in the sense of vectors, it belongs just to our D such that the norm of x bar is less than 1, right? So this is for the Klein model. And we are going to, so the idea to define the metric, so definitely the metric should satisfy the following. Then the distance between 2 points. So I have here 2 points, x hat and y hat, right? Well, this is precisely p of x, right? And I define it as the hyperbolic distance between x and y, right? The hyperboloid distance between x and y. And this is the this is a proposition or a theorem to show that then the following is true: the hyperbolic cosine of distance between 2 points x and, sorry, we close the door. So yeah, the hyperbolic cosine of distance between the points from this model, from the Klein model, satisfies actually the following. Well, it definitely is equal to the hyperboloid, to the hyperbolic cosine of distance between the hyperbolic preimages, hyperboloid preimages, right? And it can be computed. So it is equal to the following fraction. It is 1 minus x bar y bar, where this is just the Euclidean scalar product, right? So remember that my points from the Klein model, we remove out this first, okay, the 0 coordinate 1, and we're getting to vectors x bar and y bar from RD, and there we have just the standard Euclidean scalar product. Moreover, in this precisely in this with this choice of coordinates, it will be indeed a very standard diagonal Euclidean scalar product. Once you remove the coordinate x0, right, the remaining is just x1, y1 plus and so on, x d, y d, correct? So we use, yeah, so we use x bar and y bar for these coordinates. And the denominator is the square root of 1 minus, and this is also the Euclidean norm, 1 minus the square of the Euclidean norm of x, and the same for y bar. Yeah, so that's the formula for BD. Sorry, for the, yeah, for the Klein model. Okay, now about the Ball model. For the Ball model, I think we will use another notation. So let me denote this. So this was my projection P, right? So this point is U of x, while this point is, I don't know, let me use probably. I don't know. It's maybe not a good idea to use different types of letters, but let it be psi, right? Psi of x. Okay, so I'm going just to write down again the psi of x is the pair 0. Okay, and also I can also probably denote it as x bar. So let me use xy bars for standard Euclidean vectors. And we are just going to write it down. So psi is the map from HD, right, to BD. And then I'm going to write down the formula for this model. So the hyperbolic cosine of distance of the with respect to the metric B in the ball model between the points. Okay. So between the points, I did not have a good notation for them. So let it be x tilde y tilde, right? Just not to confuse. Well, generally we will denote them just x and y, okay? But in this picture, since we consider all four models simultaneously, I prefer to distinguish the points, okay? So here we have x, an element here, right? Here I have x hat, and here I have x tilde. Okay. Yeah.
So the x bar used to define and x bar used psi are not the same thing, right?
Yeah, that's actually a good point. Yeah. In this sense, yes, actually that's a good remark. So in some sense, using x bar here is not good. Yeah, and moreover here, actually x bar is also not just like a part of, right? It's not like just x with removing. Yeah, let me think about the notation. I don't know. I'm already out of symbols, I guess. X prime, maybe. Yeah, so it's not the same, not the same set of, yeah, not the same tuple of coordinates. That's very important. We will actually just compute them right now. So that's our goal. So the hyperbolic cosine of distance between the points here in the ball model is this. It is equal to 1, right, plus the fraction, and here I have 2, the Euclidean norm of, okay, so since you noticed that it should be it should be x prime minus y prime, the Euclidean norm of this vector, and there we have the scalar product. Well, sorry, not the scalar, but just the product of these two vectors, 1 minus x prime squared and 1 minus y prime squared, right? This is our formula number 3. Okay, and we will consider a bit later the formula for the upper half plane. Well, maybe let me just write it down. Okay, so we kind of have this table of points, right? So the hyperbolic. Okay, how should I denote it? Actually, I can just use the following notation, right? I think I can say that I'm using how should I denote this? Maybe Z or I don't know. Okay, maybe it's just better to write Y. Let me change the notation a little bit. So my Y, this will be just the points. Y, right? Such that Y is from RD, and I will write it here, right? It's all Y from RD, such that YD is positive. It should be shorter, yeah. So this is my X is YD, okay? So now in this picture, I'm just writing down the distance between. So I have here the standard points. So I will use the standard X and Y. This is going to be equal to the following. It is 1. So the hyperbolic cosine of distance between 2 points X and Y here is going to be also the norm, okay, the square X minus Y, the norm over 2 XD YD, right? So and now our goal is to prove these formulas. And we are going to use it just by writing down the projections. Okay, so the formula for okay, I will just write it's like a theorem, right? So this is my theorem. And our proof starts here. I think it's enough. I can move it to the top. Perhaps I will use the picture. Okay. Yeah, I didn't write that. This is my ball model, right? And upper half plane. Oh, sorry, upper half space. So this is upper half space. U, B is ball. K corresponds to Klein. Okay, so the proof is here. We let us write. Let Q be the P inverse. This is from KD to HD, right? Then I'm going to write down the formula. So then Q of X can be simply written as follows. It is just, okay, how we denoted the point. Yeah, so in fact, generally, the Klein module is just, right, KD. It consists of the points. So this X hat is the way how we embed KD in the Lorentzian space, right? So KD itself is just the set of X bar, right, such that the norm is less than 1, right? So I want to, so I'm starting with X bar, and I want to find a Lorentzian, well, a hyperboloid point. Okay, so the point is that I'm taking the vector okay, yeah, so I have a point X bar, then I write down 1 X hat, right? And then I want to well, wait, no, 1 X bar, right? So I'm writing that X hat is 1, the pair, yeah, it's 1 and X bar. So it's already D plus 1 dimensional vector. And I want to write down Q of X. And then I'm taking X bar plus let me think a little bit. Yeah, this is not enough. So again, the idea is that we have similar triangles, right? So basically, we have 2 Euclidean triangles that are similar, and the similarity is basically that point, right? So it is the, yeah, so the similarity multiple, so this factor is the quotient of the Euclidean norm of X over X bar. It seems like it should be just okay, maybe I'm wrong, but let me check. X bar plus vector 0 over the norm. Is it correct? Yes, it always has norm. Okay, let us think again. So I want to obtain the vector well, they definitely belong to the same ray, right? So it's just lambda. So my Q of X, right? Okay, let us think this way. Q of x should be some lambda x hat, right? And how I find this lambda? So it's lambda and lambda x bar such that minus lambda squared plus lambda squared, the norm of x bar is equal to -1, right? So lambda squared multiplied by x bar squared -1, it's equal to -1. So lambda squared is 1 over, okay, so lambda itself is 1 over square root of 1 minus that's okay, right? Okay, so then I'm writing down. Okay, maybe this is better just if I change. Yeah, I think it's better if I just explicitly write it this way. So we have 1 over the square root of 1 minus root x squared. And here is the pair 1, and the remaining is x bar. Yeah, that's correct. Okay, just looking at this particular computation, you will then the okay, then the hyperbolic cosine. Yeah, you will huh? Where? It should be q of x hat, right? It should be q of x hat. Thanks. So here we first add just one coordinate, right? It belongs to KD. And then q of x hat here and here, right? It is indeed equal to lambda x hat. And then it is just the direct computation. Then the hyperbolic cosine of rho k between the points x. Well, technically I should probably write not x hat and y hat. I probably should write just x bar and y bar, but it doesn't matter. So then this is equal to, yeah, this is equal to the hyperbolic cosine. So we'll just write that this the hyperbolic cosine of rho h, and here I'm writing q of okay, maybe q of x. Okay, what I wanted to say that is it is actually q of, okay, I want q to be the map from x bar to, yeah, so I want q to be the map from x bar, so it is the map from x bar to x, right? So my q of x bar here and here. So I'm having q of x bar, q of y bar. And since then we know that this is equal to minus the scalar, the Lorentzian scalar product of q of x bar and q of y bar. We basically just write it here. right? Then one can just obtain that this square root of, we obtain two such guys, but with respect to x and y. And on the other hand, so what is my point, right? My point q of x bar, it has those coordinates. So the scalar product, so I need to take the, well, I just need to take this vector and multiply it by itself, right? So I obtain minus, okay, that's complicated. I obtain 1 minus square root of 1 minus x bar squared, 1 minus y bar squared, right? And then I multiply 1x bar times 1 y bar with respect to the Lorentzian scalar product. So I need to take here 1 and x bar. So this will be the scalar product just equal to 1 minus, oh, it should be minus 1 plus, yeah, and here is 1 minus, correct. So here I have 1 minus in front of the, just before the entire fraction, and on the other hand, the scalar product is minus 1 plus x bar, y bar. And this proves the formula for the hyperbolic cosine of rho k. Okay, so this is for, so for the metric in the Klein model, it's done. Now for the metric in the Poincaré-Bow model, I suggest to write it as follows. So suppose I have a, so we have this map xi. Now I'm taking the point xi of x, right? So xi of x is like 0x prime, where x prime is the point from BG, right? Okay, then I'm taking, so so xi be, okay, let xi be from HD to BD. Here we have x, and here we have points x prime, okay? Then psi inverse of x prime can be written as follows. It is, so again, I need to write down the vector which looks like again, I'm using these similar triangles, so it should be this vector. Okay, so I'm taking this vector, right? I need the vector from this point minus a to the point in BD, which is my x bar, and basically the difference between this point and this point multiplied by some lambda will give me this point. Okay, so the idea is that I can write it as x bar plus some lambda. Again, there is some lambda. It will be another lambda, but yeah. So lambda, let me denote it as lambda prime. So some lambda prime multiplied by x prime plus, I think, the vector a, right? Ah, wait, it's not a good. How I'm adding the vector 8. So I need to take. I think I just need to change x prime here. So x prime can be written as 0. Okay, it can be written as x, how we denoted x tilde, right? So it can be written as x tilde, which is a 0 and then the coordinates of x prime, right? So here I'm writing x tilde and x tilde plus a. Yeah, is it correct? So let's look at the picture. I'm starting from the point x prime. So the point x prime, okay, this is my point x tilde, right? Over here. It is this one. So x tilde is over here. So x minus x tilde, right? X. Okay, x minus x tilde is this vector, correct? And it's scaled by some lambda is x minus minus a, right? Yeah. Remember that this is x, right? And indeed, x minus x tilde is some lambda prime multiplied by x tilde minus minus a. So we have this condition. Well, and we have another condition. So I need to write that where the scalar product of x with itself is -1. And this allows to compute lambda prime. And I'm going to write down this already explicitly. This implies that psi inverse of x prime, okay, it is the following set of coordinates. It will be here, the 0 coordinate is the fraction, is the ratio of these two. It is 1 plus the Euclidean norm of x prime squared over 1 minus the Euclidean norm of x prime squared. And the other coordinates are just 2x1 over the same guy and 2x d over the same 1 minus the Euclidean norm of x prime. So the formula for the inverse map is the same. Then it gives you the result for the hyperbolic. It remains compute the hyperbolic cosine of h of c inverse x prime and psi inverse of y prime. So I just leave it as an exercise, okay? Okay, so this was the formula for the Bow model. And again, the formula for for rho U follows from rho B, right, from the formula for the ball model, for the metric in the ball model, using inversions with respect to the sphere. So basically, it follows from rho B using the coordinate formula for the inversion I forgot how denoted the sphere, like O, capital omega, right? For the inversion that sends BD to UD, right? That's the main tool for the proof. So, right, yeah, so this gives us the formulas for these 4 classical models. Yeah, so they are all presented on this board. And like again, for computations, I would say that like the most useful is the first one, but the upper half plane model, upper half space model is quite useful, especially in dimensions 2 and 3. Okay, so this finishes the proof, right? This completes the proof. Okay, so now I wanted to say just a few words about isometries, and probably then we are done for today. So you see, again, let me remind that geodesics here are intersections of the planes in the Lorentzian or Minkowski space with the hyperboloid. And then it remains to see what are the images of those planes in the ball model, Klein model, or in the Poincare ball model. So here it is like not that simple to show that it should be so in the ball model of the Poincare conformal ball model, those geodesics are like circles orthogonal to the boundary or diameters of the ball. One can show that by actually using this map. You can see you can just find what is the Riemannian metric. So what is the Riemannian metric in the ball model just by using this? It is like some technical computation. Probably I can even do it maybe next time. But the point is that it is like it explicitly shows that the Riemannian metric here is the Euclidean metric scaled by, well, it's just basically scaled by this factor. It's like 1 over minus 1 and so on. And this fact gives you that this model is conformal. And in particular, it implies that the hyperplanes and planes from from here basically should be sent to generalized spheres in the ball model, right? But yeah, but this is like some technical statement and proof. It is a little bit out of our scope, but it's just important to understand how it. So what stays behind right behind of that? Okay, then based on that, I want to leave some remark. Okay, it's like a remark or proposition. So the group which I will denote as O prime D1, which is the subgroup of OD1 preserving HD, acts transitively on HD. In fact, it acts transitively on the vectors with negative norms. It acts transitively on the space of vectors with positive norms, and so on. But the hint to prove this is the picture. Just take a, right, so this is our hyperboloid. Let me take the point A, which is this is my point A. And let us take any other point X. So A is 1, 0, and so on, zeros. X is any other point from HD. Find the reflection. Find the reflection. Let me denote as RH. That sends X to A. And this will give you this isometry, right, acting. So in particular, so how should this reflection look like, right? That's the main question. And this is obtained by the following. So you can find a hyperplane that intersects. So you have a geodesic segment from A to X, right? And we need the bisector, the hyperplane bisector. So we need to take a hyperplane H that is orthogonal to this geodesic segment, right? So H is orthogonal to the geodesic segment. I will denote it with square brackets, okay? XA. It's orthogonal to this segment. It's just kind of like a linear algebra exercise. You can change a little bit the basis in the entire Minkowski space to make it like a little bit, okay, to make it look more convenient. And then you will see that it's always, so your, in fact, your goal is not like to write down this explicitly, but your goal is to show that it's always possible to do, right? And you will see it from this picture. So then another remark is that this group is generated by hyperplane reflections. And in fact, this proves that, so it's like part 1, and the part 2 is that the isometry group of the hyperbolic space HD is isomorphic to O prime D1. Right? This follows from this consideration. Okay, yeah. So probably next time we will continue discussing isometries in different models and probably the isometry groups. So that's the plan for this, for the remaining lectures, for the second lecture of this week. And I remind that the next week is going to be a break, right? 1 week break. It's like a reading week. Probably it's next week, right? Yeah, I will check. I don't know. But just in case, yeah. And yeah, so soon you will see the exercises for just the exercises that I left. Okay, I will collect most of the exercises that I left after during the lectures, and I will also send out the like homework assignments. Yeah. Okay, that's all for today. Thanks. O prime, well, I mentioned only this group. Yeah, and so here I'm taking the index 2 subgroup, which preserves HD. Yeah. So in fact, maybe it's better to write that it is index 2, right? Index 2 subgroup. So I do not want to interchange, right? I do not want to interchange the components of the hyperboloid. Yeah. So either I can take a subgroup that preserves this, or I can take the quotient by plus minus identity if I want to remove. Yeah. But like this is a bit more explicit. Like the projective description is more abstract in some sense, while here it's just algebraically I'm taking only those matrices that leave the upper half sheet invariant and do not send it to the minus HD. That's the idea. Okay. Yes, yes. So the O prime D1 actually acts transitively on HD. Yeah. So the group O prime D1 preserving HD acts transitively on HD. And then it follows that the isometry group of HD coincides with O prime D1. It's isomorphic to that one. Yeah. Okay. Yeah. Are there any other questions? Okay. So that's all for today. Thank you.